Hello everyone, and welcome to the introduction to natural language processing (NLP) given by Daniel Nissani. I'm Wedad Anbtawi, the organizer of this workshop on behalf of FruitPunch AI and YATS. This workshop will be recorded, so after the workshop we will send you the slides and also the recording. And please, if you have any question, put it on the chat and Daniel will answer it. So Daniel?
Hey everyone, I'm Daniel Nissani. I'm a data scientist at Cigna Healthcare, and I just graduated from Cornell Tech with a master's primarily in data science. Today we're going to talk about natural language processing. I want to give a caveat. Natural language processing is an extremely huge field. Even if I tried to give an overview where we just looked at the highlights, I think that would be like a month-long workshop. So what I'm going to focus on today is give a really high-level overview of word representations, which I think if you're a data scientist or someone who's aspiring to be a data scientist, this will be like the most natural thing that you'll probably try and think about when you're trying to solve any type of data science problem. So let's get into it. So what we're going to cover is why is natural language processing used? How do we represent words? Like I said, that's going to be the primary thing that we're worried about here. But we're going to go through some not naive, but like first iterations of how do we represent words. Then we're going to go into how do we encode the relationship between words. So looking at like how we can think words are related to each other. Then we're going to go through something called language modeling, which is the most cutting edge in terms of giving word representations. Then we're going to go through some libraries using natural language processing. Natural language processing, I think particularly in the past like 2 to 5 years, has really grown in terms of the library and open source material out there for you to get started on any project you want to use. And it's starting to rival that of computer vision. If you guys have exposure to computer vision has for a long time had some nice open source ways of using tools to solve computer vision problems. So we'll go through those same flavor of libraries that'll offer that same kind of performance boosts. And then just something that I like to do always is what did we not cover? So what are things that you should go read up on your own, or things that you should know that are in the field, but we just didn't have time to cover today. Any questions for the agenda? Feel free to post in the chat. Excellent. So I want to give some housekeeping stuff too. In order to fully appreciate this presentation, although not completely required, some prerequisites are a basic understanding of neural networks. I am going to go into a little bit about neural networks, and I'm going to assume some basic understanding. I did a presentation about neural networks last week. I hope some of those who came to that presentation are here today. If you are, hello. If you don't know anything about neural networks, I highly recommend going and learning something about them, as it'll make understanding the advances in natural language processing much easier. Natural language processing, as we'll see very, very quickly, adopts a lot of stuff from linear algebra. And so the ideas from linear algebra are important to keep in mind when we're talking about natural language processing type ideas. Also, a lot of the advances in natural language processing come from introductory ideas from machine learning and data science. They kind of drive why we would even look for a new way to represent words. And so if you've had introductory machine learning or data science experience, those concepts will come up from time to time. That'll be important. I love questions. Please feel free to ask questions at any time. Send them over the chat. I will stop mid-presentation and just read your questions. I think your questions and what you want to learn is much more important than what I'm going to preach about for the next hour. So if there are anything specific that I'm not covering, or if I'm glossing over details, as I will be doing during the presentation, feel free to answer here, and I'll try and answer them to the best of my ability. And if not, I'll definitely be sending resources and this slide deck to all of you at the end of this talk, so you guys can have that to peruse. Any questions before we get started? Excellent. Okay, so where is natural language processing used? So it's just so many places. If you have a text and you want to summarize that text into like a sentence, maybe you have a paragraph and you want to summarize it as a sentence, that's become very, very huge for natural language processing for a variety of reasons. One could just be you want a smaller number of words so you can make a feature space in a data science perspective. Other ways is just you want to be able to distill something down so you can present it in a report. There are many different use cases here. And then another way of thinking about it is also text expansion. Like, can we take a small sentence about something and expand that out into something else? Speech to text and text to speech. This is an extremely important field within natural language processing, and it also has to do with digital signal processing. For those who are unaware, we have technology now that can read us books and also translate our speech into text. This is extremely important for people who have learning disabilities or might have some type of other disability that prevents them from interacting with technology the way most of us do. On top of that, it gives different affordances to technology that we take advantage of and allow us to interact with it in different ways. Topic modeling, extremely important also. Like, given a whole corpus of text, unstructured text, can we discern what topics are in there in any type of way? Sentiment analysis, I think a lot of people are aware of what sentiment analysis is like data science, introductory data science courses usually go through this. It's just trying to gauge whether something has a positive or a negative sentiment, usually as a binary classifier, but it could also be as a multi-class problem if you have the right data. Question and answer, another really important NLP field. This goes into like chatbots would be a really big one. I think Google's working on this a lot with their Google Assistant, just being able to answer human questions where it's not just based on some rule set that you're giving it, but it can answer questions that it wasn't necessarily trained on. OpenAI has come out with a brand new innovation on this too, called GPT-3, that is able to do some amazing question answer stuff. It's a very, very popular and growing field within NLP. Text generation, so just being able to generate text, like given like half a sentence, can you generate the rest of it, or given half a paragraph? And many more. I don't want to stay on this slide for too long, and I probably have already stayed on it for too long as it is. NLP, anytime that you're dealing with language in any way, whether it's through voice, whether it's through text, anything, you're going to want to think of certain techniques of how you represent that data so that you can do these amazing tasks and many other tasks that aren't necessarily related to language. So with that, I do want to give a caveat. Although you're always going to worry about how to represent your data, where it really comes in handy, I think, from like a data science perspective is in sentiment analysis and question and answer. These are the places where I've seen like specifically trying to make some type of word representation and then working with that gets the most bang for your buck. Are there other pieces of NLP, such as the ones that I've already listed, that benefit from this? Yes. But in terms of what I'm going to be talking about, most of the innovation is within these spaces. Could I provide some examples of topic modeling? Sure. So let's say, so I worked at an ad tech company for a while. Let's say you wanted to know, we had safety categories at the ad tech company. So it was like violence, offensive language, hate speech, etc. And we wanted to know whether like our data sets were comprehensive in terms of those classes or whether those classes were good at all. So we would then put our text, they were all like web pages, through like some type of topic modeling approach. And what the topic modeling does is cluster the data, and then you're hoping that the clusters will then represent different classes that you can then classify by, that you can then code however you want. But what the topic modeling does is tell you how accurate clustering in terms of like maybe you want 10 classes, how accurate it would be to cluster them in terms of 10 classes as opposed to 5. And it would give you a sense of what topics would be within each cluster. So they'd like give you printouts of like the highest priority words. Before I move on to Miriam's question, Julio, did that answer what you were, was that a good enough example for topic modeling? Great. Sure, you can ask, yeah, I think it's more appropriate to ask that in terms of at the end of the presentation, Miriam. But if you see anything within the presentation that like triggers in your brain, like, oh my God, I want to know about text mining right now, feel free to ask. And if you can nuance that question a little bit, because I just want to make sure I'm answering that question correctly, that would be great. Cool. These are fantastic questions. Any other questions before I move forward? Fantastic. Cool. So let's move on. So we're going to start with a really basic example. And what I want you to take away from this example is that there are like a couple of primary things whenever you're doing a natural language processing task, whenever you're doing one. It doesn't matter how sophisticated your technique is, you're going to have some vocabulary that you're going to have to worry about. And that vocabulary is going to determine how you're going to process your words. So in this case, I'm giving like an extremely small vocabulary. Usually how you generate this vocabulary is you would go through your training data set. You'd pick out all the words from your training data set, and that would become your vocabulary that you're going to work on. There are other ways of doing it too. You could take like the whole dictionary if you want, but there are data storage issues and things like that. And you want to really make sure that you're representing your training data set. So in train time, you have everything going on there. So we're going to start with this very, very small vocabulary. Hello, my name is Stan. Not okay, said Sam. Okay, that's our vocabulary. We have 2 sentences here. Hello, my name is Stan, said Stan. And then I hate you, Stan, said Sam. Okay, those are our 2 words, 2 sentences. Now, I'm going to now represent these words in terms of a vector. So now I have this vector here where sentence 1, I have all the counts of all the words that that appeared in sentence 1. Notice that Stan, I'm going to just count it twice because I saw it twice. And then sentence 2, I'm going to do the same. This is called a bag of words. And it's a very popular first step. Like if you just don't know what to do to represent your text data and you're like, I just need to do something. This is like where you would start, is just trying to do basic counts. Now, what's wrong with this representation? Like just, or what's something you can point out that is like iffy about this representation for those sentences? And if you want, I can go back and forth too, if you want to see the sentences from before and then the sentences now. Just feel free to share in the chat. I'll give you guys like a little bit of time to think. All right, I don't see anything coming through the chat, so I'm going to go over some of the issues with this representation. So if we look at this, we have, hello, my name is Stan, said Stan. Oh, here we go. Is seems to be a filler word. That's a fantastic thing. Is in the vocabulary? Yes, it is. So is a filler word, so maybe we want to get rid of that. That's definitely something. Anything else that's wrong with this representation? There's something else that we can say here. Pointing out is really important. We're going to go over that in a sec. Okay, so I'm gonna go talk about the other issues with this, and I think the primary issue to see here, there are words in the second sentence that aren't represented in the vocabulary we have. So we don't encode them in our vector that we make in terms of our counts. That's a bit problematic, and it's something that a lot of NLP techniques struggle with, is how do you deal with out of vocabulary words? Since the second sentence does not has words that are not contained in the vocabulary, the other issue we have is that there are a lot of zeros. This vector, although not quite there yet, might be something that we would call in data science a sparse vector, meaning a vector that has very few data points that are non-zero. And that's an issue because that means we don't have a lot of really accurate data about that particular data point. So we will always want to be cautious of things like this and think about things like this when we are representing our text data. And we want to find ways to try and mitigate that and think of how to combat these types of happenings. I'm really happy someone brought up is. Did anyone else want to say anything before we move on to the next part? So much to say. And if you don't see it now, you'll definitely see it later. Great. I don't want to put you guys too much in suspense. So we really want to think about how we're representing words. So one thing to think about when we're representing words is like, okay, what if we have words that are like run, running, ran, eating, eaten, ate, eater, name, naming, named. If we had a slot in our vector for each of these words, such as if we did it for eaten, eating, ate, eater, then we'd count them as one in each slot. The problem is some sentences might have eaten, some sentences might have eating, some sentences might have ate, some sentences might have eater, but all of them have the root that they're really talking about, which is eat. Someone's eating something, someone's eaten something. It really all comes down to eat. And when we're trying to get meaning out of text, we don't want to have all of these superfluous tenses and ways of changing words from noun to verbs. We just want to be able to say eat is the primary semantic definition that everyone's trying to focus on within that sentence. The reason why we care about this so much is because we don't want to end up with the curse of dimensionality. The curse of dimensionality, just as a brief description, means if I have an extremely large feature space, it makes it harder and harder to find out when things are really similar to each other, and thus it's really hard to discriminate between things, and thus it's really hard to classify. Moreover, the curse of dimensionality is on par with sparsity. Usually when you have really large feature spaces, you're going to also have sparse vectors. Although they're not exactly the same, it's something to look out for. And you can imagine if we had eat in these 4 different ways, then we would have much sparser features for these 4 different words. And so we want to compact them into one feature so that we can get more of a richer count when we're going through it. The way you would do this is through stemming and lemmatization. Not something we're going to cover here too much now, but we're going to go over packages that'll be able to do that really easily. It's just something to keep in the back of your mind. Now we get to the comment about is. What is the problem with these words? And I know that's a little bit of a leading question, but there is an issue with like these types of words. Just put them in the chat. Like what would the issue be with these words here? Yeah, Miriam, can you say more on that? You're right to say that they don't carry any meaningful data. And if anyone else wants to chime in too, why don't these words carry any meaningful data? And think of like a really simplistic description. Don't overcomplicate it. Yeah, oh, that's a great way of describing it, Cynthia. They need other words to make sense. In other words, they carry no semantic meaning. They are literally used just to join words together. Yeah, filler words is a great way of putting it. They have no semantic meaning of their own. So they just are there to connect the words within the language, and every language has this. Words that are just there to connect things so that when we speak them or write them down, they are easier to read and make sense of. Now, this is actually an open problem. And I know that sounds silly to say, but it is. What do we consider these types of words? And we call these words stop words. That's the formal name that's used within the community. So what do we consider stop words in language is very much an open problem. I remember when I was working at the aforementioned ad tech company, we tried to create our own stop word list because for our content domain, certain words were going to act as stop words, even though in another content domain, they might be extremely meaningful. And so thinking about what is the appropriate set of stop words is not a open and closed problem. It's something that you really need to think about within your domain, what may be a stop word. Now, there are libraries out there that'll give pre-made stop word lists. And I'm gonna show you those at the end of the presentation. Are those stop word lists definite? No. Are they good places to start so you can start getting a feel or at least get these really basic ones out? Yes, they're great ways to start out that way. But the fact that this is not like an open and shut case where it's like we know what a stop word is and everything's good to go makes it so it's hard to figure out which words should we take out and not even consider when we're making our word vectors. So one way, in the very naive sense, and we're starting with the naive so we get a sense of what's going on, one way of dealing with these is just remove them from the vocabulary. Don't have them anymore. And just have the words that are going to have some type of semantic meaning to the corpus of text that you're going to be working with. So really excellent. Thank you, guys. So now I want to talk about this idea of having like a whole bunch of texts, not just looking at a couple of sentences, but having actual texts. So these are Amazon reviews. Let's say we were given like 1,000 Amazon reviews. We don't know we don't know their rating. All we have is the text attached to the Amazon review. What we want to predict, okay? So we have some label data, and what we want to predict is whether it is a positive review or a negative review. You can make this into a multi-class problem, right? Where it's a rating between 1 and 5. But let's just make it really simple. Is it positive or negative? Period, done. And can we predict that from just the text? Now, what we might think about is, okay, well, we can make these really long bag of word vectors, which will encode all the things, all the words within the reviews. But we might start hitting like the curse of dimensionality. I imagine the vocabulary will be really huge. And we might also start hitting the fact that some words may appear within a review more than other words. And we want to make sure that those words are actually given the appropriate weight. So for example, maybe we had a review of a smartphone, and like this is a great example where we have galaxy as the word here. Maybe there's another review reviewing the smartphone where galaxy shows up like 10 times. But these are just generic reviews. They're not necessarily reviews of smartphones. So should galaxy be given a weight of 10, or should we consider the rest of the texts that are out there? And this is where we get to the idea of term frequency and inverse document frequency vectors. Term frequency talks about measuring the frequency of a word within a review. So if we were to go into one of those Amazon reviews, we would just measure how frequent is that review, is that word within the review. Then we would offset that score by looking at what's the frequency of the word in all of the reviews. In other words, if I take all of the reviews in aggregate, and I'm just looking at how often the word shows up in each review, can I then offset how many times it showed up within a specific review? There's specific mathematical formulations for all of this, but those are not the most important thing. Definitely something that I'm going to give you in the resources. But the big takeaway here is, instead of just having raw counts, let's actually think in context. How many times has this word showed up in a certain review? And then how often does it show up in the whole entire corpus of reviews at all? And then offset that. Cool. Any questions about those two representations right now? Cool. So I have a question for you all then. What are the limitations of bag of words and TF-IDF? What would the limitations be of these? So we tried everything we can. We get certain accuracy scores out. What are some things that we think about that is like, oh, something smells fishy here in terms of what we know about language? And feel free to think on that for like 30 seconds to a minute. Oh, that's a great one. So how do we handle negations? I think is more as a general thing. So Miriam said maybe a certain word is preceded with not, and maybe there are other negations we need to consider too. That's a great point. Okay. And I actually want to talk about Miriam's point more. Notice that she's talking about the word not and it preceding another word. As a little bit of a leading question, do bag of words or TF-IDF have any of that information about where words are placed? Yeah, Cynthia in big bold letters said, no, they do not. And that's a really big thing here. So to formalize what Miriam and Cynthia are saying right now, bag of words and TF-IDF, they are making an assumption about language that we should be a little bit skeptical about. They're essentially saying language is IID, independent and identically distributed. So we're putting that assumption onto language, and we're essentially saying these variables, which we'll call words, are independent of each other and don't actually determine whether one is going to happen after the other. As people who speak any language, doesn't need to be English, just any language, we know that that assumption is false. We know that when we're speaking something, we have a set of words that after I utter some half of a sentence, there's some set of words that are more likely to come after that part of that sentence than other words. TF-IDF and bag of words are not making that assumption. So what we want to do in our next iteration of making better word representations is we want to think about how can we encode the actual relationship between words within sentences. And we're going to go through various methods of how to do that. And they're going to get more and more complicated as we go. But this is the idea that kind of spurred the next iteration of what's going on here. So what I want to look at now is this project. So this is very pretty. This is a word cloud, if you will. These are called word vectors. This is the next iteration of what people have done. And the way that they're going to assess that kind of relationship between words is they're going to do something called word similarity. Okay, so in the chat, give me some words. We're gonna see whether it's in the corpus here, but don't think of anything too complicated. Just give me like some basic words that you would wanna see. Once you type it in the chat, I'll type it into this thing and we'll see what's related to it. Let's see, is like in here? Like is in here. And let's get the just 5 nearest neighbors. So things that are like, unlike, such, other, and including. So based on how this data was trained, these are the words that are most like. Now let's look at success. So if we look at success, popularity is really big. Successes is really big. Sales. So maybe whatever corpus that this algorithm was trained on, there were a lot of things about sales and being successful at sales. So sales is in here. Failure, successful. The other thing to notice about the similar words here is that this corpus, whatever they didn't lematize or stem. So those methods of trying to make everything into just success are really just for TF-IDF and bag of words. We've left that world now. Now we're just worrying about, okay, what about just words in general? Can we not do all of this stuff because it's hard to do and it's not necessarily that, it's clunky, it's not the best thing. Can we just have the words? And this is the second time where we saw with like, unlike was very similar. Failure is similar to success, which means they both have similar semantic meaning. They just are opposites of each other. And those we still want to seem similar to. Any other words you guys want to try out? These are really good ones. I think while I'm waiting for those, my favorite one is looking at king, because that's just the example that I had. Kings, queen, throne, son, emperor. I think my favorite thing is that queen shows up here, which if we think in terms, not that we should think of gender as binary, but if we just take that on assumption for a quick sec, this is like having that same opposite feel of male meaning a male ruler, king meaning a male ruler, and queen meaning a female ruler, and so we have that type of dichotomy there. I guess if you're using that language, it's just having a sex binary, which we shouldn't necessarily think that way either. But this is really cool. And then I also want to look at like how they're doing this comparison. So they're doing a cosine similarity here, which we're going to talk about a little bit. This is a Euclidean similarity. So they're looking at Euclidean distance being the way that they're measuring things. Notice that they're not sorting it by Euclidean distance, and that's for a very specific reason that we'll talk about a little bit in a sec. Cosine is more what they're using, what you should use for your similarity vectors. So this is really cool. So this is what we call word vectors, and word vectors are the next really big important way to think about things. And I think before we go and jump into actually how word vectors are established, I want to kind of drive it home with this example, so we really understand what they mean by similarity. So let's say there's this person, Jay, and two other people, and they all took like a Myers-Briggs test. Okay, Myers-Briggs is a personality test that assesses you on 5 different traits. So you get assessed on these traits, and at the end of the day, I want to know how similar I am from someone else. You might have remembered from linear algebra, these are vectors. And these vectors can be of varying sizes and can have some varying angle with the terminal axis of the x-axis. And we want to think about here, what is the better measurement? Is it better to measure the angle between the two vectors to establish similarity? Or is it better to establish the distance between two vectors? I'm going to claim that it's better to establish the angle, because if I were to use distance, then I could have some very, very short vector that's very close in angle to another vector that's very, very long. And so if we use distance, we would get some distortion here. So we want to use the angle to be able to establish what does it mean to be similar. So if they're closer in angle, they're more similar to each other. So when we go and do that, we use a cosine similarity metric. The way that the cosine similarity works is you're just using that cosine function that you learned in linear algebra, which has to do with the norms and the dot products of certain vectors. And using that, you can then establish some type of score. And as you can see here, person 1 is going to have the higher score because they had the smaller angle between them. And so that's the cosine similarity metric. Why am I talking about this? Well, when we have words, we want to be able to establish a similar type of similarity. We want to be able to say whether words are similar to each other. And I think the big question right now is, well, what are these features going to be for these words? How are those going to get generated? So this is where the algorithm word2vec comes in. And the way that word2vec works is that it's going to look through like the sentences that you give it. You're going to give it some sentences, and then it's either going to do a continuous bag of words, which means it's going to try and predict the center word based on some number of neighboring words. And that window size can be whatever you want. It could be 1, which it is right now. It could be 2, 3, 4. It could be however large you want. You're just going to have to worry about computation time. And then the other one is another one is skipgram, where instead of predicting the center word, you're going to predict the neighbors based on the center word. Either one is a representation you can use. If I am remembering correctly, which I might not be, skipgram I think has a bit more, has higher levels of efficacy, like it's just more accurate. But either one was a huge step up for NLP in terms of trying to process words and think about how to represent them. And when you do that, you can start having a cool algebra once you get your word vectors out, like king minus man plus woman equals queen. If you start playing with the word vectors that you get out, you'll be able to see this kind of algebra develop. Any questions before we keep on moving on? This is like the crux of like this big development that happened in NLP. Cool. So what is word2vec? Like as an algorithm, what does it look like? So what word2vec is it's really just a feed forward neural network. The continuous bag of words, like we said, we take the neighboring words, however many we want, and we predict the center word. So that's why the input has a ton more words than the output. The output's just a single word, while the input is the neighboring words that you put in. Whereas skipgram, you just take the center word and you're trying to predict its neighbors. And that's in terms of a neural network diagram. That's how this kind of shows out. I want to look at skipgram a little bit more because I want to hit home something about where these word vectors come from. So let's say I have this one word, ant, and I now want to know what's the probability that any of the 10,000 other words within this one hot encoded vector will be a neighboring word to ant. And so these are all the words that maybe will have that. So this is what the output layer is giving, is those probabilities. We pass them through this hidden layer and then do a dot product to assess that similarity, which is what the objective function is to train on that neural network. But the reason why I'm focusing on this hidden layer is because let's say I want to take out those word vectors. Let's say I want to see what those word vectors are, not just see the probability that a word may be a neighboring word, but I want to know what are the actual word vectors. The hidden layer actually gives me the word vectors. So the hidden layer becomes a lookup table where I can just grab those vectors, any of the 10,000 words I have, and I'll get whatever number of neurons or number of features that my hidden layer had. I'm going to be able to grab that size vector. So in this case, for those 10,000 words, I'd be able to grab a 300 sized vector. And a really nice thing about Word2Vec is that 300 neurons, it doesn't need to be 300 neurons. I can make it 1 neuron. I can make it 1,000,000 neurons. I can make it whatever size vector I want. So in terms of combating, for instance, the curse of dimensionality, I can start combating it right here. Of course, you're going to want to do some experimentation to see what size is best. But the big thing to take away here is once I have this neural network, I can just grab the word vectors right from that hidden layer. And then I can use them however I want, for classification, for clustering, for anything, which is a really powerful thing to have. Cool. So now we want to think about the limitations of word vectors. And I think it's going to be harder to think about what the limitations of word vectors are if I asked you. So I'm just going to talk about what the limitations are. This is a great question. So Miriam asks, how does it differ if you had 10 neurons or 10,000 neurons? That's a fantastic question. So this gets to the idea of, let's say I have 1,000 words in my data set. Whatever sentences I put in, there are only 1,000 words that come out, okay? Then if I only put in 1,000 words to get really trained on for my algorithm, and I make the size of the neurons 10,000, that means my word vectors are now 10,000 large. I highly doubt I have enough data to tune only 1,000 words for 10,000 neurons. I'm probably going to get some really strong overfitting, or I'm going to get some underfitting that's going to happen because I'm not really going to be able to measure out the words. So I'm just going to have randomness and noise. Whereas maybe for 1,000 words, I want to do 100 neurons because I'd be able to train those neurons more accurately because there are less features for me to try and train out. So you want to try and balance it with your data set size and the number of neurons you have. And this is just a general thing for neural networks, is you just want to make sure that you're not blowing up your feature space, because then it's you're priming your algorithm either to overfit because it can't really find any signal. And so it's just overfitting to your data, or underfit because it's not able to represent the features very well. Does that make sense, Miriam? Let me know if you need me to say more. Great. Any other questions before I go into limitations? That was a really excellent one. Fantastic. Okay. So what are limitations of word vectors? So one limitation of word vectors that I kind of swept under the rug is, how do you deal with out of vocabulary words? So if I have a word that's out of vocabulary, what can I do to deal with that? There are some smoothing techniques we can talk about. There are some ways of dealing with them. Maybe you want to tokenize. There are tons of ways to do it, but at the end of the day, you need to think about how do you do it? And that's not inherent to the word2vec algorithm or other word vector algorithms of the same flavor. So we want to think about how do we really do that? What's going to be the ways that we're going to try and do that? The other thing we need to think about is, and we saw this when we were playing with the diagram, is we're going to have to worry about words like success, successes, successful. All those really mean are success. And although it's nice that they came out to be similar to each other, what that means is that success is fitting to other words that really mean success also. And we might want success to be more akin to other words like something you could succeed in. And so we want to be able to try to make sure that we're not just fitting to the exact same words in different flavors, but that we're trying to see relationships between words come out in these similarity metrics. And then the other thing that we haven't talked about at all that's extremely important in terms of limitations of word vectors is this example. So I have two sentences here. One is, I'm going to go sit at the table. Okay. So in that sentence, the way that I'm using table is, one, table is a noun. Okay. Table in this instance means some hard surface that I'm going to be able to place something on, that people congregate around usually. Maybe if you're not congregating around it, it's still a hard surface you can place something on. Maybe I'm going to sit at it. Maybe I'm going to stand by it. But it's a noun. It has a certain definition. It has semantic meaning. That's very different from the second sentence where it says, let's table this conversation for now. Tabling that conversation, that's a verb. Tabling that conversation. What does it mean? It means I'm saying, let's hold off on this. It has no real semantic likeness to the way table was used in the other sentence. So even though word2vec was super powerful, this conundrum could never be solved because in one instance, table is being used as a noun in a very specific way. And when I go and I do my fitting in my neural network, it's going to try and be very similar to things like sit, stand, put down, maybe if you want to think about a phrase. So maybe down is a word that it's going to be very close to. Food might be something that it's very close to. A notebook, things that you would use a table for. Writing. Whereas table this conversation is going to be close to very other different words. And what this is going to do is confuse the fitting of the algorithm. And you're going to get this word vector that's been trying to fit to too many different ways that the word could be used. But at the end of the day, you're only given one vector for that word. So how can we expect that this vector is going to be very good, no matter how long we train it for, if it's going to keep on being pulled in too many different directions to actually make an accurate vector? This is where the next innovations come in terms of language models. What language models do at a high level, and I want to stay high level with language models because they get very complicated very fast, is they create word vectors that are very specific to the certain context that they're in. So as an example, stick can mean I'm stuck to something, like I'm sticking to something, or I stick something onto something, or it can mean like I have a wooden stick, or let's stick to improvisation in this skit. That means let's stay on this. This is now using it in like the more abstract way of using stick. Those are all different definitions of stick though. And what language models will do is they'll try and create context word vectors. Dynamic word vectors is another way of putting it. And these dynamic word vectors are going to change based on the context that they have actually been in. And that's the key to try and elevate what our word vectors were before to the new level of word vectors we have now. So Elmo, and also this is going to look like we're just going through Sesame Street, and I apologize. The NLP community and just machine learning in general got a lot of flack for these very complicated names, and so they just started using Sesame Street characters. I apologize for the comedy. Sesame Street, I mean language models, like Elmo, came in and did this great thing. So how does Elmo work? So here we have Elmo. Elmo works with LSTM layers. LSTMs are a type of RNN. I'm not going to go through the architecture because that would be a whole other talk in terms of how LSTMs work. But LSTMs are a type of RNN that take care of vanishing and exploding gradient problems. And what this is going to do is it's going to try and predict what the next word in the sentence is. So this is going 3 words in, so let's stick to, and now we want the next word to be improvisation, and what these LSTMs are able to do is try and make that prediction based on some labeled training set. And they do this because they're state-based machines, so they're able to remember previous words that were put in to try and think what's the next possible word in this. So how does it do it? It does something called bidirectionality. So it's going to go in one direction, and then it's going to go in the other direction. And in this instance, it's trying to think of how we're going to get the word vector for stick. So it's going to go in one direction through the sentence, then it's going to go through the other direction through the sentence, the forward and the backward language model in this case. It's going to concatenate the hidden layers within both language models. And then that's going to be multiplied by some weights. And those weights, once we sum all of that up, we get our new word vector for stick. So this is how Elmo works. And the big thing to take away here, I think the really big thing to take away is that what we're doing here is we're trying to see how can we capture context within a sentence. One way of doing it is by reading it forward, reading it backward to see how is that word situated within that sentence. Capturing all of that information, we're then going to create some word vector for it as it pertains to that sentence and then get something out. The next innovation was Bert. So Elmo got tossed aside. Bert came in all grouchy and being like, I can do this better. Not going to go through the details of Bert too much. It is a transformer-based architecture. A transformer-based architecture is an encoder-decoder neural network with self-attention heads. All of those words probably don't mean much to you. And the reason is because they aren't hard to explain, but it would take a long time just to get down what everything is going on in there. The big thing to get out of here is that they replaced LSTMs with this transformer architecture, kept the bidirectionality by having it encode in one direction and decode in the other. And instead of just trying to predict a word and predict every word in the sentence, what they're going to do is they're going to take the data, they're going to mask 15% of it. You could do any percentage of mask, but I think they optimally found that 15% was good. They're going to mask 50% of it, and then they're going to try and predict the masked words. And so in this way, they're going to be able to tune the word vectors that they have by predicting those masks. And the better that prediction, the better our word vectors are going to be. Even more so, there's also going to be a way for it to understand whether a sentence should come before or after another sentence. So while it's going through its training, it's going to be able to say, hey, sentence A should come before sentence B. And likewise, sentence B should come after sentence A. And it'll be able to make that discerning task easier. The big thing to take away from Bert, and I'm sorry I'm not going through more detail. Happy to answer more questions as much as I can at the end of the talk. But the big thing to take away from Bert is that it is now the cutting edge. There are other models that claim to have beaten it out, but essentially what Bert has turned into is the equivalent of what computer vision still has, what computer vision has. a model where we can do transfer learning on because of how well trained it is on some corpus of words and be able to take those and use them for many different tasks. And BERT has been trained in many different ways. There are so many different iterations of it. There's Albert, there's Roberta, there's BERT Lite, there's, or not BERT Lite, DistillBERT. BERT has several different variations of the model, all with different accuracies. But the big thing to take away here is if you really want to be a heavy hitter, like if you want to just skip all the beginner stuff and just go use the best model, this is a really good place to start in terms of trying to use the quote unquote best thing out there. How is fine tuning done? Fine tuning. So Miriam's bringing up a great question. This is how BERT is trained. Once you have BERT, it's just a pre-trained model that you can use, and then you're going to want to fine tune it to a task. Miriam, this can be done with like your own training data, and I'm going to show a library that does this really easily, but essentially you're just going to feed in that data and try and fine tune those vectors or fine tune it for whatever task you have. So if you have a specific task, you'll train either another neural network that uses that, or you'll fine tune the whole thing. I'm going to show the library. I think they're going to do a much better job of explaining that. So now I want to show a bunch of libraries that are going to be really useful for you all to know when you're exploring this stuff. NLTK is probably the best thing for anyone trying to begin natural language processing type tasks. So in NLTK, you'll get, this is where you can get corpuses of stop words if you really need them. This is where you can get things that'll help you do stemming and lemmatization. This is really good if you want to do like classical NLP type things, or at least what has become classical NLP type tasks. This will be a really great library for you. sklearn, if you're a data scientist, I don't know how popular this opinion is. If you're a data scientist, you should know sklearn. sklearn is a great general data science package, and they also have some really cool, really nice tools for just like basic NLP tasks. So some of those tools include, I want to see whether they talk about in this tutorial. They have a count vectorizer, which you can think of as almost like creating like a bag of words for you, and things like that. I'll get to that question, Miriam, at the end. They have count vectorizer tool, which is almost like doing a bag of words. They have a TF-IDF tool that you can use to get TF-IDF vectors. Insanely useful library for models, for feature engineering, etc. Absolutely recommend it. Oh no, yeah, stay up there, please. Then we have Spacey. I'd say Spacey's something that a lot of, that's used a lot of in the industry. I don't know if they use it in a lot of data science courses. I remember I wasn't allowed to use it in my data science courses. I had to use NLTK. Spacey is where I go to, is one of my go-to things now, mainly because it is very fast and has a lot of models and things that I really would want to use. Really, really great for anything you want to do, from language translation to getting some simple models. Like I just used this recently to get some very basic word vectors out. Really, really just easy to use and good library. GenSim is another great library. Here you can use tools that'll do topic modeling. They have some tools in here for, sorry, that's my dog. He's having a fit right now. Topic modeling is something that's used a lot for. It's also used if you want to get word vectors out, or any other type of any other variations of word vectors. There's something called doc2vec if you want to do it on documents instead of words, which we're not covering in today's lecture. But this is another really great library that you can kind of like peruse and go through their API. Flare is another really good one. It's, as you can see, it's just some GitHub repo. But if you want to just grab the GitHub repo, it's really, really powerful. I actually didn't know this. Mariam, I inadvertently answered your question. There's a great biomedical data set in Flare, but Flare is great for most NLP tasks, and they start getting into the more advanced models too. So if you want a library that's using more advanced models, this is a great one. And they even do tasks that I'm not talking about today, like named entity recognition, part of speech tags, etc. So Mariam, I don't think this fully answers your question, and I intend to go through it, talk about it a bit more, but it seems like this library might be something you want to go through. Then we have Hugging Face. Hugging Face is a startup that is looking into how they can use the most cutting edge NLP techniques to make like a chatbot. I think that's what they used to be. I think they're really just a research organization now. But they have all of these models. Oh man, is this not going to be the API? Let me look for it really quick. Hugging Face API. Here we go. So they have some great documentation on all the latest models. And like I said, there are like a ton of models, so many models that have come out. But they have not only documentation, but they have integration of all of these models into PyTorch or TensorFlow. So if you want to use your favorite deep learning framework, and go ahead and use these models. They're free, they're open source, they're pre-trained. All you need to do, like Mariam is fine tune them to whatever task or data that you have, and you're good to go. So these are the 6 libraries. Those links are gonna be sent to you both in the presentation and when I send things out. But these are like some really, really important and good libraries to have to start with. And they're also used by and large by a lot of data scientists that I work with anyway. They're very popular libraries right now. Okay, what we didn't cover. We didn't cover so much. Oh my God. We didn't cover named entity recognition. Named entity recognition talks about how can I go through a text and be able to identify words, like specific words that may be names of something. Like how can I do that? Not an easy task. BERT has made it a lot easier, but not an easy task at all. Text summarization, text expansion, text generation, translation. How do we translate from one language to another language and back? Open problem. Google's been working on it for decades now. It is a very important problem. We're getting better at it every year, but it's still open. It's still something that needs to be worked on, and it's still something that's super important in the community. There are so many other tasks that I'm not bringing up here, but these are just a handful of them that you might think of when you're thinking of NLP. Architectures, XLNet. XLNet was a transformer-based model that everyone thought beat out BERT, and then they found out that you just need to tune BERT in a different way, and it beat it out. GLOVE is another word-to-vec model that's a little bit different. They usually call them global vectors. I forget exactly why. It's not something I've used a ton, but it's a really popular model. Fast text is from Facebook. It is another word-to-vec model, primarily used for sentences, but is very powerful because it's able to deal with that whole stemming and lemmatization problem that we were talking about before. GPT-X, I put the X there because there's been so many GPTs that have come out of OpenAI. There's GPT, GPT-2, and GPT-3. GPT-3 is the latest one. If you look on Twitter or on any social media where data scientists are, you'll be seeing all these like posts where GPT is having full conversations with people and is actually doing like a really, really great job. GPT-3 has been very much talked about in the past couple of months since it's come out. Many different variations on BERT. I've already talked about like the names of them. Really, these variations have to do with the number of parameters that the BERT model has, and it also has to do with the corpus that it's trained on. and it also has to do with exactly how it was tuned and what vocabulary it has for tokenization. Lane-Dirichlet allocation has to do with topic modeling. So this is a very popular topic modeling algorithm. I think it's pretty much standard whenever you want to do topic modeling. GenSim has an implementation of Lane-Dirichlet allocation that you can use. I've used it a bunch of times on different tasks. It does really well and gets out what you want, and so much more. There are so many different architectures. I mean, we haven't even spoken about the different linguistic tasks that we might be interested in, such as part of speech tagging. How do you know what part of speech a word is? Such as creating sentence graphs and making sure those sentences make sense when they're being output. I mean, there are so many different tasks and things and models to think about within the NLP community that it would be impossible to cover in the short time that we have together today. But just to keep it on your radar, these are the things that we missed out on. And at the end of the day, the biggest thing before you can do any of that is just how do you represent those words? All of them have different ways of doing it. So there's going to be, sometimes you're going to be using BERT or Word2Vec or TF-IDF. Maybe that'll be enough for the problem that you're dealing with. But sometimes you're going to have to do something different in order to represent those words. Sometimes it's just going to be something the model wants in terms of how the API was created. Or maybe when you're creating a model, if you're ever creating a model one day, you're going to need a different type of representation in order to be ingested by the model. But these are the things we didn't cover. Cool. So before I have any questions, I want to answer Maryam's. Yes, and Cynthia, I actually want to then combine yours with Maryam's. And Maryam, I'm going to probably give an unsatisfying answer. I'm not sure whether there's a BERT model that exists right now that has been pre-trained on biomedical data. And the reason why I'm talking about pre-training more than fine-tuning, and this also relates to Cynthia's question about slang and jargon. Oh, great, BioBERT exists. That's fantastic. So if there's BioBERT, that's great. So what I want to do say about any content domain, if there hasn't been a pre-trained model like BioBERT, and you went out to use vanilla BERT on biomedical data, or if you went out and used BERT on, let's say, you scraped a bunch of text from 4chan or Twitter, there's going to be a lot of slang and jargon there, right? And then you just try to use vanilla BERT. What's going to happen is BERT has a very truncated vocabulary. I think the largest model that I've used anyway only has about 120,000 tokens. And so when it's trying to understand words, what it's going to do is going to break down those words into different tokens. And those tokens are then going to create is going to help the model understand what kind of word vectors to create. Now, this goes to the out of vocabulary problem. What if I have a word that can't be broken up into those tokens? It's going to get something called an unknown token. And that's going to then present an issue for the model because it's going to get just the standard token everywhere. That's what would happen if BioBERT didn't exist. But Maryam, I'm super happy to hear that BioBERT exists. But as a general caveat, whenever you're thinking about it using these more advanced models, and this goes to the first thing I said in the beginning of the presentation, be aware of the vocabulary that your model is trained on and that it knows about. Because if it doesn't know the vocabulary that you're going to be using, then it's just going to be that much harder for it to capture the signal that is the noise within NLP data, natural language data. Cynthia, did that address your point as well? I'm just making sure. And Maryam, I'm super happy to hear about BioBERT. I hope it's trained on the exact data set that it will help you with whatever you need to use it for. It is a research area. Like, what is the best vocabulary to use within models? I'm not too privy about the advances within that research area. I think you're definitely right that it could be, and I think it is. I know it's something. Let's just say this: the 120,000 tokens that BERT has are not random. They are trying to find the best, most comprehensive corpus of data, corpus of text. So the text that they're going to use to train the model, that's going to give them the best generalizability for as many tasks as possible. I think the research area that another research area that we could think of that would be very important is it better to have like, so Mariam, before I get to your question, just as a research area, is it better to have one giant model that's going to be able to do every task we want it to do on any type of corpus? Or is it better to have smaller models that can do very particular tasks really well? And I think that's something, I don't know how much it's being researched, but it's definitely something that I think the community is grappling with in terms of what we want to do. And at least from what I've seen in terms of the research coming out, in terms of new models that are being developed every year, it seems like there are more models coming out now that are trying to do every single NLP task under the sun, rather than focus in on a certain task or set of tasks and become really good at that. But we'll see. I think you're definitely right, Cynthia. It's something to definitely consider. So you're confused, Mariam, you said you're confused about the difference between BERT and FLAIR. Yeah, slang does change all the time. To answer your question, Mariam, BERT is a model. BERT is is like, yeah, model is the best word that you can say. It is a pre-trained model that then you can use to either get word vectors, which are traditionally called BERT vectors, that you can then use for different tasks, and you can fine tune that to your data to get better BERT vectors. FLAIR is a library. So FLAIR may have, I'm not actually aware whether FLAIR has a BERT model, but FLAIR is a library of different models that can be used for different tasks. So that's the difference between FLAIR and BERT. Does that answer your question? So FLAIR, like, I think a better way of thinking about it, FLAIR is more analogous to Hugging Face, and BERT is a model within Hugging Face, within the Hugging Face library, just like BERT could be a model, but I'm not sure, could be a model within the FLAIR library. Does that make sense, Mariam? Great. Any other questions? These have been fantastic. Really enjoyed them so far. And I think, and I also think the questions so far are going to help whoever's listening later in the recording understand. Yeah, please, Mariam. We have time, so like feel free to ask more questions. And I again apologize for my dog. He is now sprinting around the apartment. He's very like energetic right now. So the question is, what is the difference between dictionary tagging and text mining, NER, and how BERT deals with NER? And for those who are uninitiated, NER stands for named entity recognition. I am actually not sure what the difference is, but I can speak to how you would do an NER task with BERT. So you'd create BERT vectors for each of the words. Let's say you're doing tweets. This is where I've used it before. You have a bunch of tweets and you want to start picking out prominent figures that are being brought up in tweets, maybe politicians, for instance. and you have some training corpus that you already know who's a politician, and you're training on that. So the BERT vectors then become the representation of your words, and you would use some, and I've also concatenated that with part of speech tags and other small things just so we could get out more signal. And then you would run like a multi-perceptron on those vectors to then classify whether that is a politician or not. So that would be like the named entity recognition task there when you're using BERT. I'm actually not privy to like how the dictionary tagging and text mining works. So I'm sorry, I can't speak to the difference. But that was a great question. Any other questions? So Cynthia, thank you for thanking me for the session. And she says, I tried to concatenate words to find meaning in data mine POS and open source project I did. Yeah, it's interesting. I'm actually talking to people at work right now, and they always, and they've been telling me recently that they're very surprised how like you add one piece of information, like one feature vector to your vector, and then you start getting huge increases in performance. And I think because of my experience with natural language processing, it's something that like, it's huge. Like the minute you just start getting the right pieces of data in, you just see drastic increases in performance. So thank you for coming, Cynthia. And actually thank you to everyone for coming. I'll wait on the line for a couple more questions, but if I don't see any come in, thank you all so much. I hope this was helpful, and I hope it was informative. And I hope it'll help you at least get started with NLP. I know I brushed over a lot of details, but that was more in the interest of brevity than anything else. Happy to talk more. I'll be sending my email along to everyone, and I hope you have a great day. So I'll stay on again if you have a couple more questions, because I think we still have a little bit more time. But if you need to go, you're free to go.
I think there's no more questions.
Yeah.
So thank you, Danielle, for this amazing workshop and the previous one also. And thank you guys for attending. So we will send you later an email about this workshop, the slides, and also the recording. And in case you have any more questions, please email us and we will make sure to answer you. So thank you, and I wish you a nice weekend.
Yeah, thank you, everyone. And actually, I forgot to put my email on the slide. I just realized, so I'm just going to put in the chat. Feel free to email me with any questions, or if you want to like collaborate or talk or anything like that. Happy to link up. So thank you, everyone. Have a great day.
Bye.
Bye.